Hello, in this lecture we are going to derive a mathematical model that corresponds to a theoretical game. And the means to do that is by using ordinary differential equations. There will be non-linearities. They may, uh, they may bring some resemblance. There will be some similarities with the mathematical models that we studied for interacting species, especially the nonlinearities for interacting species models. These mathematical models for theoretical games are typically referred to as replicator equations. So this brings us back to some things we mentioned before, but we mentioned them here briefly. And the three main ingredients that define a game in the context of game theory. The first of these ingredients are the individuals that are engaged playing this game, and they are referred to as players. They're the participants of this activity called a game, a theoretical game. The players are involved in the game because they are playing a set of options. The options they have to behave in this activity, and these are what are called strategies. So each player plays a strategy during the game. And the goal of the players is that they engage in playing these strategies because they are going after the goal of maximizing their payoff. So each player receives some type of return, um, and it may depend on the strategies that they are playing. So game theory explores how players are going to behave in a given game. So now we turn to evolutionary biology. The genes of an organism strongly determine the characteristics that are considered observable, such as traits and phenotypes, etc. So the genes also define the fitness in a given environment. Organisms that are more fit will tend to yield more offspring, um, or causing genes that provide greater fitness to increase their representation in the population. Um, and you may have heard, I mean, this goes back to the angle of evolutionary biology that we are revisiting here. And you may have heard the phrase survival of the fittest. And definitely that survival of the fittest translate into a large or higher or advantageous fitness, and therefore this notion that organisms that have a better fitness have the tendency to have a reproduction rate much larger, and the genes that provide greater fitness will increase the representation in the population. So that's the nature in action. So feeder genes tend to win over time because they provide higher rates of reproduction. Many behaviors involve interactions of multiple organisms in a population. The success of any of these organisms depends on how its behavior um, interacts with the behavior of others. And the fitness of an individual cannot be measured in isolation. The fitness has to be evaluated in the context of the entire population in which the organism resides. Um, so let's start working on the derivation. Okay, so let's start throwing some symbols here. Suppose we have a type S and a type T in a population. Okay, And the fitness for type S here in red is, we're going to give some values here, is fitness 2.5 versus the fitness of type T, which is set for this example to be 1. Don't worry about what these values, what are the units of these values. This is just to make a point that will be clear in just a few seconds. So constant selection means that fitness does not depend on the composition of the population. Also, fitness does not change over time. So the fitness of S being 2.5 is a lot larger than, well, is larger, maybe not a lot, but is larger than the fitness of T, which is 1. On the other hand, frequency-dependent selection means that the fitness depends on the relative abundance of individual types. Okay, so maybe I can point a couple of things here. So um, constant selection, we're saying here constant selection means that fitness does not depend on the composition of the population, and the fitness under constant selection is not changing over time. Okay, constant selection. However, frequency-dependent selection means the fitness depends on the frequency of individual types. Frequency being the relative abundance, how many of those types are around in the population. Suppose that type S has the ability to move, okay, to move around. And this type S here in red has that little thingy there that allows that organism to move around, okay? And if few others are moving, then type S has a larger fitness than type T. If many others are on the road, you know, they act like a roadblock or something. Uh, well, not many others. Many others moving are on the road. This meaning that there's a lot of traffic. Okay, then the fitness advantage is reverse. Okay, so this was an illustration of two types and how the fitness, uh, may depend on the relative abundance of the types. And now we're gonna derive some equations. So we're gonna use some notation. We're gonna say, hey, let's use the subindices here to denote the frequency of one type and another type. So those with type S are going to be quantified by x sub 1, and those with type T are going to be quantified by x sub 2. And x1 and x2 are functions of time, so at time t, we have x1 of t, and we also have x2 of t. We're going to store that in a vector x, so x has entries x1 and x2, and we are going to use one type of payoff matrix here. In fact, we're going to use the two-player payoff matrix. And well, we're going to use one of this type, but remember that when you have a two-player payoff matrix, you can easily translate that matrix into what we call the strategy payoff matrix. So you can read this matrix, say organism 1 versus organism 2 is S playing as organism 1 gets A, organism 2 gets A. So that means that in this table, we write A on this first entry in the 1-1 entry. This information would go onto the 2-2 entry, and then we have organism 1 with S versus playing against organism 2 with T. Organism 1 gets B and organism 2 gets Z, so we have B on entry 1-2 and C on entry 2-1 of this strategy payoff matrix. So once we do the translation, we are going to do the following. So we're going to consider that vector that has the frequencies of individuals with one type and another type. And we're going to do a matrix vector multiplication. Okay, matrix vector multiplication. We're going to take this 2x2 matrix multiplied by that vector. That's going to give us a vector. The first entry of that is what results by multiplying these. That's what results by multiplying this row times that column, and so that gives us this entry here, ax1 plus bx2, and then we multiply the second row times that column, and we get the second entry. So important thing is that this vector here is going to be considered a fitness vector, a vector that stores the values of fitness, and that vector depends on the densities of individuals in x1 and individuals in x2. So this is a case of density dependent fitness. So in this case, we would say the average fitness is given by a weighted sum. You could choose to say if you wanted, let's just add up F1 plus F2. This would be a sum of total fitness. If you say, add these two values and then divide by 2, that would be an average value. But what we are doing here is expressing F1 times X1, F2 times X2, where X1 is a weight for the value of F1, and X2 is also weight for the value of F2. So that's a weighted average. So we substitute F1 and substitute F2, and the average fitness here is denoted with this symbol. So an important observation is that X1 plus X2, they denote densities or frequencies, so they are proportions, and then they add up to 1 at each time point, each time step. So F1 minus phi, it's a calculation that we can do here, F1 minus phi, and we're gonna have to do some algebra, and we can rearrange that like this. And then we have a term here, 1 minus x1, which 1 minus x1 will be x2 given because of this, right? So you can you can easily see that x2 equals 1 minus x1, and then that helps us in making this expression a little, you're just doing some simplification, algebraic simplification, and we can also compute here f2 minus phi. We do more substitutions and end up with this term.